Lecture 20, Evolution of High Mass Stars, Part 1. If you're still with us, which you are, you'll know that we spent the last 3 lectures talking about the evolution of low mass stars, of which 97% of the universe's stars are. But, as I promised, there are another 3% of high mass stars, so those stars greater than 8 solar masses. And as I have sort of teased you with several times over the course of the semester, there are some important differences about the how those stars evolve, the reactions that occur, and the ultimate fate that awaits those stars at the end of their stellar lives. And so, I've told you that it's exciting. I've told you there are some differences that are of interest. And finally, you've stuck around long enough to start hearing what some of those differences are. So let's dig in. So you've seen this slide before, but it really sets the stage for what we're going to talk about today and during the next lecture. And the point is that you can divide the main sequence into 2 main groups, by no means equal, right? As I've said, 97% of the stars are low mass stars. But this other 3% are what we're talking about now. And the reason that we choose that 8 solar mass dividing line is again not to have equal numbers, but because what happens to these stars when they run out of nuclear fuel, in other words, what the evolution of these stars look like, differs in important ways from the low mass stars. So today we're focusing on the upper left-hand corner of the HR diagram. These are O and B class stars primarily, and they are, well, not primarily, that's what they are, and they're the hottest, most luminous stars in the universe. So bottom right-hand corner, all these 97% of low mass stars, we're now experts in those. We know everything there is to know about those stars. Not really. You could spend a career focusing on more details, but we understand the basics of their evolution. So now we're focusing on again these high mass, 3% solar, 8 times solar mass stars. So why are these stars different? Why does it make a difference what the mass is? Well, as I've said a number of times, almost everything about a star is determined by its mass. And we've talked about several of these things, but just to kind of remind you and set the stage for what we're going to focus on today, when a main sequence star is less massive, that means, so when gravity was forming that, that low mass star out of the interstellar medium, it's going to be smaller, right? Because there's less stuff there. It's going to be cooler because the heat, remember, the heat that turns a star from a protostar into a star comes from the gravitational potential energy being converted into thermal energy. Well, if you have less mass, you have fewer atoms, then you have fewer collisions and less gravitational potential energy. And so the star is cooler. It's redder, which is a result of it being cooler, right? Because we know from the Boltzmann distribution that and Wien's law in particular, that the peak wavelength is inversely related to the temperature, and so hotter stars, or not just stars, but hotter objects, give off a black body radiation with a shorter wavelength, which means higher energy, and bluer. So these less massive stars are redder, and they're less luminous, right? Because again, the Stefan Boltzmann law says the luminosity is proportional to the 4th power of the temperature, and so if the temperature is lower, the luminosity is lower. So these low mass stars, they were smaller, they were cooler, they were redder, and they were less luminous. Okay. On the flip side, when you have a high mass, star on the main sequence, it's going to be bigger, it's going to be hotter, it's going to be bluer, and it's going to be more luminous, right? So we kind of got the 97% of the boring stuff out of the way, and now we're finally focusing on this 3%, these large, hot, blue, and luminous stars. And one reason that this hotter is important, other than just to say, oh, look, it's hotter, is that, as I've mentioned a few times throughout the course, nuclear reactions, fusion reactions in particular, are more efficient at hotter temperatures, so they occur more quickly. And this is generally true. So if you've taken chemistry before, for example, you may have learned that chemical reactions tend to occur more quickly at higher temperatures as well. And so if you have a reaction occurring slowly, you heat it up and it tends to make that process go more quickly. Well, exactly the same thing is true in the fusion reactions. And a simple way to understand it is just that temperature, remember, is related to the average speed of the nuclei as they fly around in random directions inside the plasma in the star. And so the hotter the star is, the faster those nuclei are flying around, the more frequently they collide with one another, and that's how reactions occur. So it's a pretty, I mean, again, there are lots of details that you could go into, but that's a simple picture that basically gets the important aspects of it. So the reactions that do occur are going to occur faster. But as we're going to talk about today, it turns out that in addition to that, new reactions that we haven't talked about become possible with these higher temperatures. And so it's very similar to the fact that we said in order for the proton-proton chain to be initiated, for that set of reactions to occur, the hydrogen plasma needs to reach temperatures of around 12 million Kelvin, right? That's the minimum temperature, that's the threshold for which the proton-proton chain begins. And so if a protostar can reach those temperatures in the core, then it becomes a star. And if it can't reach those temperatures, then it just kind of fizzles, becomes a brown dwarf, and does not become a true star. But there are other reactions that, other than the proton-proton chain, that require higher temperatures to occur. That are not realized in low mass stars, but are realized in high mass stars. So there are two things that we're going to talk about that are implications of the higher temperatures obtained in high mass stars. One is that reactions we've already talked about, like the proton-proton chain, occur faster. The second is that reactions that we haven't talked about yet, because it wasn't hot enough for those reactions to occur in a significant way, those are going to occur now. And so let's talk a little bit more about that. And so we're going to talk in detail about that, but just to sort of give you the bottom line here is that while the proton-proton chain is the dominant set of reactions in low mass main sequence stars, it turns out that those reactions, while they still exist, while they still occur in high mass stars, they're actually no longer the dominant ones. The dominant set of reactions in high mass stars are known as the CNO cycle, and we'll talk about the details here very shortly. The end result is going to be the same. We're going to convert 4 protons or 4 hydrogen nuclei into a helium nucleus, and we're going to release energy along the way. But the details of that process will be different, and the amount of energy released will be different. So let's look at the life cycle from a high level now. Stars begin their lives, or before they're born, right? They begin forming in giant molecular clouds, which, as we've talked about, are one of the coldest aspects of the interstellar medium. A little bit counterintuitive, right? But it has to be cold in order for enough mass to condense and collapse sufficiently to turn into a star. So these stars form in giant molecular clouds, and eventually ignition occurs in the stellar cores, and they are born as stars on the main sequence. And they live on the main sequence for some period of time. And that period of time, as we've talked about, varies wildly, right? For low mass stars, it can go from 500 billion years, at the coldest M-class stars, to something like 10 billion years for a sort of a G-class star like the Sun. And then for O-class stars, the most massive stars, they can burn out in as little as 1 million years. So we've talked about the wide disparity in terms of lifetimes, but they live as a main sequence star. And then eventually, when the nuclear fuel is spent in the stellar core, they evolve off the main sequence and they expel material back into the interstellar medium. And that can occur in a couple of different ways. One is in the form of planetary nebula, as we've talked about, and the other is the possibility of type 1a supernova, for example, which we talked about last time in the context of binary stars and white dwarfs exceeding the Chandrasekhar limit. And so if that doesn't ring a bell, go back to lecture 19 and feel free to review that. But that's what we've talked about so far. And then what's exciting, and the reason that I can call this a life cycle, not just a lifetime, is that when that material is ejected into the interstellar medium, whether through a planet in the form of a planetary nebula or a Type 1a supernova, that material goes out and can play a role in seeding star formation in other giant molecular clouds. For example, in the case of a supernova, the extreme speeds at which that material is sent out into the interstellar medium set up a shock wave which can heat up gases, interstellar gases, extremely quickly, and can actually again initiate star formation in that way. So now let's talk about the CNO cycle. So again, the thing to remember is that the CNO cycle is for high mass stars what the proton-proton chain is for low mass stars. This is the dominant set of nuclear reactions that fuel the star. And what's interesting, and this is what the C stands for here, right? C is carbon. And not to spoil the whole thing, but the N stands for nitrogen and the O for oxygen, right? So before you know anything about it, the details of this reaction, you know there's carbon, there's nitrogen, and there's oxygen involved. So the first thing to say is that in order for the CNO cycle to occur, you need to have some carbon present in the star. Not very much, as we'll see, because it will not be consumed. What it will do is serve as a catalyst for the reaction, which something you may be familiar with from chemistry. A catalyst is just an element or a molecule. It's something that speeds up the reaction, but is not consumed in a net way. So, and we'll see the details here. But if you have a little bit of carbon in the star, and the star is big and hot enough, if it's greater than 8 solar masses, then we get this new type of nuclear fusion reaction that we haven't talked about yet. And again, this is the CNO cycle. And so this is the high-level view. There's always a high-level view, and then there are always multiple steps when you dig down into the details. But at the highest level, we take a carbon-12 nucleus, which is that's the most normal sort of most common type of naturally occurring carbon. Has 6 protons and 6 neutrons in it. We're going to take that carbon, we're going to add to it 4 protons and 2 electrons. Remember, the electrons are always around there because we form a star out of electrically neutral interstellar gas, right? So for every positive charge, every proton, you have an electron. So we take a carbon-12 nucleus, we take 4 protons, we take 2 electrons, we do a bunch of stuff to it, and then we spit out a carbon-12 nucleus, a helium nucleus, 2 neutrinos, and 7 gamma rays. Okay, and of course that's a lot of energy in these 7 gamma rays. So you see there's a carbon-12 nucleus on both sides of that equation. So you might be inclined to just cancel it out, and you could in a net sense. But it turns out that, as we'll see, if it weren't for the carbon being present, this would not happen at all. So the carbon is critically important, but also critically important is the fact that it reappears, after the reaction. So that's important because then it's left around to initiate another set of reactions and another set of reactions. And that's why you don't need very many carbon nuclei for this to occur, because the carbon's not being consumed, it's just speeding up the process. It's enabling the reactions to occur. But once you know that, if you sort of block out the carbon-12 nuclei from this picture, you see the result is very similar to what we saw from the proton-proton chain. We're converting 4 protons into a helium-4 nucleus or an alpha particle. Because we're transforming 2 of those protons into neutrons, we also produce 2 neutrinos. And if you remember your proton-proton chain, you'll remember there were 2 positrons involved as well. Well, those positrons effectively cancel out the electrons that came in on the left side. So again, we'll see the details. But this is the highest level picture of what's going on in the CNO cycle, which again are the dominant reactions for high mass stars. So just to summarize again here, carbon is a catalyst for this reaction. It means it's not consumed, it just makes the reactions possible and speeds them up. So now that we've got the high level CNO cycle out of the way, we can dig into the details. And I know you would have preferred me to start with this, so I apologize for delaying it, but here's the fun that you were waiting for. The first step in the CNO process, starting in the upper left-hand corner, involves the collision and reaction of a carbon-12 nucleus with a proton. So when that occurs, so that, remember, there's not a lot of carbon in the star, but there's enough, and there are lots of protons, obviously. So you're bound to have this collision occur. When it does, the carbon-12 nucleus essentially captures the proton and is thereby transformed into a nitrogen-13 nucleus. You know it's nitrogen because now it has 7 protons, and if you look at your nearest periodic table, 7 protons means nitrogen. It's nitrogen-13 because you have a total of 13 nucleons, 12 from the carbon nucleus, and then the additional proton. But it turns out that nitrogen-13 is quite unstable, and so it quickly decays, radioactively decays, into carbon-13 by emitting a gamma ray and transforming one of the protons into a neutron. Okay, so that leaves us with a carbon-13 nucleus, which then quickly encounters another proton, and it captures that proton, and is thereby transformed into nitrogen-14. Well, that nitrogen-14, and a gamma ray is released. Right? That nitrogen-14 nucleus quickly encounters another proton, is transformed into oxygen-15, which emits a gamma ray in that process. So energy is being released at every step of the way. That oxygen-15 is unstable. It is transformed, it radioactively decays into nitrogen-15 by converting one of its protons into a neutron. And then finally, that nitrogen-15 collides with yet another proton, and eventually produce, in that reaction, you just have a rearrangement of the nuclei, and out on the other end spits out again a carbon-12 nucleus and a helium-4 nucleus or an alpha particle. So more steps here than in the proton-proton chain, but you can see that there's a recurring theme, and that recurring theme is something, whatever there is, whatever heavy nucleus there is, starting with carbon, it hits a proton, and then something happens, and energy is released. And of course, in a couple of these stages, here at the carbon-13 stage, and then again at the nitrogen-15 stage, you do have a transmutation of a proton into or a neutron into a proton, which produces, again, the familiar positron and neutrino. And we've seen this in the proton-proton chain. Anytime a positron is produced, it quickly annihilates with an electron that's sitting around, and both of those particle masses are converted into gamma rays then. So again, several details here, several steps, but you'll see a lot of familiar things. Obviously, the big addition here is the carbon, and just as I promised, you start off with a carbon nucleus, you end up on the other side with a carbon nucleus, and so the carbon-12 really is a catalyst. It's not consumed here, and once this reaction is over, that carbon-12 nucleus is free to go off and catalyze additional CNO reactions. Okay, so I could spend a lot of time talking about this process now, but now that you know the process, basically it's going to go on for a long time. It's going to go on until the hydrogen is gone, right? Until the hydrogen in the core is gone. And so the next question is, well, what happens when high mass stars leave the main sequence, right? So the high mass star sits on the main sequence for some amount of time. The CNO cycle is converting hydrogen into helium, and eventually all of the hydrogen is gone. We know what happens then. Just like for low mass stars, the radiation pressure disappears in the core, and so gravity collapses the core. And as that happens, the star leaves the main sequence, But the way in the track that it sort of traces out on the HR diagram is a little bit different than what we've seen from low mass stars. Low mass stars make a track that's shown here in red. And, the details of the track vary upon, is this a really low mass star or is it really an intermediate mass star? But generally, they go up and to the right. So the stars are getting bigger, they're turning into red giants, and they're becoming more luminous even as the temperature falls. High mass stars do something different, and they leave the main sequence almost horizontally, which is kind of interesting because what it means is that the temperature is steadily falling, right? You can see higher temperatures are at the left, lower temperatures are at the right. And so if we have this main sequence, this massive main sequence star, it's going to leave the main sequence almost horizontally to the right. So temperatures are falling, but the luminosity is staying very constant. Okay, it'll wiggle a little bit, but it's basically constant. And so what that means is that since the temperature is falling, the intensity of the light being given off, according to the Stefan-Boltzmann law, decreases, again with the temperature to the fourth power. But the radius of the star is increasing in almost exactly the right way to cancel out that effect. So the temperature is falling, but the surface area is increasing, and those effects tend to cancel each other out so that the total luminosity, the total energy production per second out of that star is essentially constant. And it's important to note that just like a low mass star, while it's leaving the main sequence, a high mass star fuses helium to form carbon on this horizontal branch. So we call it a horizontal branch because it's horizontal, but it's important to note that it's becoming redder, right? We don't call it a red giant branch, though you really still, you might still be able to get away with that because it is getting larger and it is getting redder, but the luminosity again is staying very similar. Now that we've discussed the HR diagram, let's step back a little bit and look at the schematic picture of a massive star's development as it leaves the main sequence. So while on the main sequence, a massive star is burning, in a nuclear sense, hydrogen in its convective core, right? So in the core, hydrogen is burning, is fusing to form helium, and outside the core, there is the always present non-burning envelope. So you have this hot hydrogen plasma, but it's not hot enough for fusion to occur. When the hydrogen fuel is exhausted in the core, as you're used to, the core collapses. But importantly, in a massive star, because the star starts out hotter, as soon as the core collapses, when it's finally stabilized by electron degeneracy pressure, it is already hot enough for the triple alpha process to begin fusing helium to form carbon. So, and that's an important difference between these high mass stars and low mass stars. If you remember, in a low mass star, the core collapses, but when it's stabilized by the electron degeneracy pressure, it's still not hot enough for helium fusion to occur. So in that case, we had hydrogen fusion reinitiated in a thin shell around the core, and that had to go on for a while in order to heat up the core to the point of the helium flash. That's not required for high mass stars. For these high mass stars, they're already very hot, and so all it takes is that additional heat generated by the core collapse to initiate the fusion of alpha particles to form carbon. So as soon as that occurs, then we have a couple of different types of fusion occurring. We have helium fusing to form carbon in the core, and we have hydrogen burning to form helium in a shell surrounding it. And then again, we have a non-burning envelope that takes up the majority of the star's volume. So what happens next? Well, after a little bit more time, on astronomical scales anyway, all of the helium is consumed in the core collapses again, and a new set of reactions starts. This is important because if you remember low mass stars, the fusion stopped at this point. A low mass star never got hot enough to fuse carbon, which is why a white dwarf is a degenerate sphere of carbon and oxygen, because the carbon and oxygen just aren't hot enough to fuse even in the core of the star. But these massive stars are hot enough that that fusion can occur. So whereas we would have ended life as a planetary nebula and white dwarf at this point for a low mass star, something different is going to happen. So pay attention. So at this stage, after we collapse the core a second time, we begin immediately fusing carbon to form a few different elements, most notably sodium, neon, and magnesium. And as you might imagine, there are different sets of nuclear reactions that produce those products. Fortunately for you, we will not go into details of what those reactions are. You just know that carbon is fused to form sodium, neon, and magnesium, but we're not going to talk about the particular nuclear reactions. So that's what's happening in the core. And then there's a shell surrounding that core in which helium is fusing to form carbon, and there's another shell around that in which hydrogen is fusing to form helium, and then finally there's the ever-present non-burning envelope. What do you think happens next? Well, eventually the carbon is exhausted in the core collapses again, and what do you know? You start fusing the sodium, the neon, and the magnesium to varying degrees. And so the upshot is that eventually you get to a stage where this thing looks a whole lot like an onion. You've got a degenerate iron core in the center, surrounded by a layer in which sulfur and silicon fuse to form iron. You then have another shell in which oxygen is fusing to form sulfur and silicon. You have a shell in which neon is fusing to form oxygen and magnesium. You have a shell where carbon is fusing to form sodium, neon, and magnesium. You've got a shell in which helium fuses to form carbon. And then finally, you've got an outermost fusion shell in which hydrogen is fusing to form helium. And then finally, you have the non-burning envelope. Now, this is not drawn to scale, as so many things in this class. If you look down here at what the scales really are, this multi-layered onion-like core is now about 1% of the sun's radius. Okay, so all of those different layers are packed into a sphere, which is about 1% the size of the sun. On the other hand, the total radius of this thing is about 1,000 times the radius of the sun. So this is wildly not to scale. The core has a radius about 1/100,000th of the entire star. So the vast majority of the volume of this star is the non-burning envelope. It's just a hot hydrogen plasma that's, sitting around. But there's a lot of interesting stuff happening in this small core. And so a lot of layers, a lot more layers than ever occurred in low mass stars. But it's important to highlight here, and we're going to talk more about it. This fusion process stops at iron. Okay, so the last, you form iron, that iron collects in the core, but you're not going to fuse that iron. And we're going to talk very shortly about why. But before we do that, I want to come back to the HR diagram and show you what some of these tracks look like as stars of different masses leave the main sequence. So starting down at the bottom right-hand corner, we have a 1 solar mass star. So this would be the sun, for example. And you've seen this before. It goes generally, with a little wiggle here, it goes generally up and to the right. So it's cooling off, going to lower temperatures, but the luminosity is going up substantially because it's getting much larger. And it follows that track until it hits the helium flash, right? As you increase the mass of stars, the shapes of these tracks get a little bit more intricate. You have more wiggles and so on, but they all, and they tend to flatten out, right? Eventually you get up to a high mass star where the track leaving the main sequence is almost horizontal, as we've already said. So lots of details. As always, there are people that spend their careers and their lifetime studying these details, but mercifully, this is going to be enough for us. Okay, so now I want to come back to something that I just pointed out a couple of slides ago, which is This fusion for high mass stars stops at iron. Okay, why? Okay, so the core of a red supergiant, and it's a supergiant because it was formed out of a high mass star. So this high mass star was already very large, and now it's gotten really gargantuan, as it has left the main sequence. So you've got this onion-like structure. Remember, this is wildly not to scale. If I drew it to scale, you wouldn't see anything. You would see a dot for this onion-like core, and then everything that you would see would be the non-burning envelope. But the core here is iron, and it's labeled inert iron core here just to highlight the fact that it's not reacting, it's not fusing. So far, we've gone through level after level after level of different fusion reactions, but it stops here at iron. So why? And the answer has to do with a concept known as the binding energy of a nucleus. So the binding energy, fortunately, is basically what it sounds like. It's the energy that holds a nucleus together. So another way that you can think of it is if you were to take 2 protons and 2 neutrons, and you were, that were far away from each other, and you were to bring them together, they would form an alpha particle. They would spontaneously combine to form a helium nucleus. And when they did that, they would give off energy. The amount of energy that they give off is known as the binding energy. It's also the amount of energy that you need to put into the nucleus if you wanted to break it back up. Okay, so that's the binding energy. So what I want to plot for you now is the average binding energy per nucleon as a function of the number of nucleons in a nucleus. So what I mean is the number of, let's talk first about the horizontal axis. The number of nucleons in the nucleus is fairly straightforward. It just means how many, if you add up the number of protons and neutrons in a nucleus, what number do you get? So on the low end, we have hydrogen 1, right? 1 proton. That's the smallest nucleus that exists, and that you can't get any smaller, right? On the other end of the axis, we have uranium. For example, uranium is the largest atomic number element that is stable or metastable. Uranium does actually, it's naturally occurring. We can mine it, and we do mine it. It is radioactive, so if you wait a sufficient number of billions of years, there won't be any uranium left on Earth, but it's going to take a long time. So and if you look at uranium-235 or U-235, for example, it has, not surprisingly, 235 nucleons, and so it's up here near the upper end of the spectrum. And then in between, we've got all the other elements. So that's the horizontal axis. On the vertical axis, we have this average binding energy per nucleon. And so what that is we take the binding energy of a nucleus, and then we divide that by the number of nucleons. And so essentially you're saying, well, how much energy per proton or neutron is holding this nucleus in? So it's a measure of how tightly bound the nucleus is. And what you'll notice is that at low nucleon number, this plot jumps up very rapidly. Not surprisingly, hydrogen 1, a proton, does not have any binding energy because it doesn't take any energy to combine a proton with nothing, right? But as you start adding additional protons, this plot jumps up very quickly. It then reaches a plateau, reaches a peak at iron 56, which is the most common isotope of iron, the most naturally occurring one. It's has 26 protons because every iron nucleus has 26 protons, and it has 30 neutrons. After iron, you can see the plot turns over and decreases gradually. So it doesn't decrease sharply like it increased sharply over here for low nucleon numbers, but it does decrease. And so what this means is that iron 56 is the most stable nucleus in the universe. There is no nucleus that is more stable than iron. As you might guess, this has something to do with why the nuclear fusion starts with iron. Fusion is a process in which light nuclei are combined to release energy. But in order to get that energy release, you need to be forming something more stable. Taking 4 hydrogen nuclei and combining them to form a helium nucleus releases energy because you formed a more stable nucleus. It has slightly less mass, and so some of the mass, just a little bit, but enough, is transformed into released energy through Einstein's equation E equals mc squared. If you wanted to go back the other way and break up helium into hydrogens, because you're starting from less mass and creating more mass, you have to put in that extra energy. Iron is right in between well, it's right in the middle, right? It's the most stable point on this plot. And so what that means is if you take light nuclei and use them to form iron, you will release energy. But if you take anything heavier, if you take iron or anything heavier and try to put them together, you'll make something less stable and you'll actually have to put energy in. Put it another way, moving upwards on the diagram releases energy, and moving downwards on this plot requires energy, which means that you can't get any better, you can't get any more energy out of your nuclei than by forming iron. Any nuclear reaction involving iron fusion would require energy taken in instead of releasing it. It would take energy out of the system, it would cool it down, and so it will not occur naturally. You could accomplish, in the laboratory, for example, you could accomplish fusion with iron, but you would have to give it extra energy. That's not what nature is going to do, and so the result is that when these high mass stars produce iron, it stops there and the iron just sits there in the core. So now that we understand everything about the nuclear processes that fuel these high mass stars, let's take a look at the periodic table and ask which elements have we been able to create so far, both in the low mass stars that we're now experts in and in the high mass stars we're talking about today. Well, we know to begin with that we started out with hydrogen and helium, right? The interstellar medium is made up of about 90% hydrogen, 10% helium, and so that came from a very early stage, and we take as given that it exists in the interstellar medium. Once we use that hydrogen and helium to form small stars, those stars go through the proton-proton chain, the triple alpha process, and produce a number of other elements, including carbon, nitrogen, oxygen, neon, and sulfur. Not in equal amounts, right? We focused, it's mostly carbon and oxygen that's produced in the, and that's what's largely left in the white dwarf that we've talked about. But there are other reactions that we haven't talked about that do produce a few other elements, including nitrogen, neon, and sulfur. So these are produced by small stars. Now that we know about large stars, we can fill out a little bit more. And I won't read off all of the elements that we produce in large stars. We've talked about a lot of them, but as always, there are additional elements we haven't talked about yet because they're produced in smaller quantities, and we don't want this class to turn into, a class in nuclear physics as much as I would enjoy that. So between the Big Bang, which produced hydrogen and helium, large stars and small stars, basically we now have most of the first 3 rows of the periodic table, though there are a few notable absences, right? If you squint really closely, you can see that we haven't produced lithium or beryllium yet, and we haven't produced boron yet. So those are notably absent. And then, of course, there's a whole lot of periodic tables still to go that's beyond iron that we haven't formed. And so keep that in mind, because the question is, well, where is that stuff coming from? But so we'll come back to that question of where the larger or the higher Z elements, as we call them, the elements with higher numbers of protons come. But I want to talk a little bit about timescales too, because, and I mentioned this before, with each stage of stellar evolution, the star evolves more quickly. Each stage takes less time than the last. And so for some prototypical high mass star, you might take 7 million years for hydrogen burning in the core to occur through the CNO process. Once that completes, once all the hydrogen is gone from the core and it collapses, the triple alpha process takes only about 500,000 years, or 500,000 years, to consume all of the helium. Once that's done, it takes maybe 600 years for all the carbon to be consumed, maybe 1 year for the neon to be consumed, 6 months for the oxygen, and as little as 1 day for the silicon. So it's really remarkable that we start off on these astronomical timescales, and the pun isn't intended, but it's, we call things astronomical for a reason, because these, we have these mind-boggling numbers. But by the end, we're talking about taking a day to burn up all of the silicon in the core. So each stage really gets much, much faster. And kind of the pinnacle of this process is that when the iron core becomes too massive, if it occurs, you get too much iron there, gravity takes over, it wins against the degeneracy pressure, and it collapses, and it can collapse in less than a second. So we're really on very short time scales now. Well, what happens when that core collapses? Well, nothing stops it, it turns out. And so much like we saw in a type 1a supernova, in which a white dwarf exceeds the Chandrasekhar limit, collapses, and then bounces back out and explodes, we're going to have what's called a core collapse supernova here, which is what it sounds like. The iron core becomes too massive, it collapses and bounces off, and is an extraordinarily large, very high energy explosion. So, and the process is very similar to what we've talked about before. The electron degeneracy pressure cannot balance out the gravity, because it's become too massive. But what's interesting about this process is this is the first time that neutrinos actually become important. And I've mentioned this, I've alluded to it a few times already throughout the series of lectures, because I've said normally we just comment, yeah, these neutrinos are there, they need to be there to, for the nuclear physics to work right. That's how God made it, to put it shortly. But we don't say anything more about them. But now we're going to say something more about them. So as the core collapses, the core temperature becomes so high that thermal gamma ray photons, which means just the gamma rays that are there just by virtue of how hot it is, they initiate a process that's known as photodisintegration, which is, if you break it down, photo has to do with photons, right? So it's these gamma ray photons that are initiating the process, and disintegrate, So to photodisintegrate just means that nuclei are being broken up by these photons. Meanwhile, neutrinos stream out from this collapsing core because of all of the reactions occurring. The core then becomes so dense that the electrons are actually absorbed by protons. So now these electrons, which up until now have just been sitting around minding their own business, now it becomes so dense that the electrons and the protons and the nuclei get pushed together, they get squeezed together, and the protons and the electrons form neutrons, and that gives rise to all of these neutrinos, right? So these neutrinos now are flying out like crazy, and that's actually why they're finally important enough, because there are so many of them, and the core is so dense. So then this photodisintegration and the electron absorption combined, they sort of steal the internal pressure that would otherwise exist. Because remember, the core up until now has been supported by electron degeneracy pressure. Well, you're stealing these electrons now, which means you're decreasing the internal pressure. And so the collapse that's already occurring speeds up. And it speeds up until these nuclear forces suddenly become repulsive. In other words, you're squeezing these nuclei together so tightly that they actually rebound. And when that happens, the core bounces out at just an absurdly high speed, sends a shock wave through the rest of the system, and just completely annihilates the vast majority of the star. And so that kind of brings us down here to the bottom here, where the The shock wave passes through the outer layers of the star, blasts all of that stuff out into the interstellar medium at near the speed of light. And this is known as a type 2 supernova. So we talked about a type 1a supernova, which occurs when a white dwarf exceeds the Chandrasekhar limit and explodes. This is a core collapse supernova, or a type 2 supernova, which occurs in high mass stars when the iron core becomes too massive to be supported by the internal pressure. When this occurs, you spread throughout the interstellar medium a lot of higher Z elements. In other words, sometimes they're called higher Z elements. Z represents the atomic number. So in other words, all of the neon, the silicon, the sulfur, the oxygen, the iron, all of these nuclei that were produced during the star's lifetime are now sent flying out into the interstellar medium. But there is a small remnant which can be left here. And it is quite small, and it's small in this diagram. But if you look in there and you squint, you can see it's labeled something that sounds kind of exotic, and it's known as a neutron star. And a neutron star is something that we will talk about in more detail later. But we are finally getting to the exotic, exciting aspects of astrophysics, as if this whole series of lectures hasn't been very exciting. But so stay tuned for more on the neutron star. But the neutron star is the remnant that is left after a type 2 supernova, just like the white dwarf is the remnant that's left after the sort of the natural evolution of a low mass star. So let's come back now to our periodic table and say, well, we had produced several elements, right? Most of 3.5 rows of the periodic table during the lifetime of low and high mass stars. What do you think might have happened? Did anything interesting happen in terms of element production during this supernova? Turns out the answer is yes. A huge number of additional elements are produced during the supernova itself. In fact, almost everything else in the periodic table. You can see if you look down at the lower right, there are some things down here past plutonium that are artificial, that we have not observed. So these are man-made elements that we have not observed in measurable quantities coming from nature. In all likelihood, they actually are produced in these. You can almost guarantee they're produced in some small quantities from supernova, but we just can't measure them. But the point is that in these supernova, you're forcing everything together. Things become so dense in the core that you just flood these nuclei with neutrons. And even though these nuclei are not very stable, they can't help but form because everything is so densely packed. And so people can and do, again, spend careers looking at the details of these higher element production in stars. We will talk a little bit more about that going forward. In particular, we'll talk about something known as the R process, where R stands for rapid, because the production of these higher Z elements is very rapid as the supernova occurs. But we will not talk about that today. So that actually brings us to the end of part 1 of the evolution of high mass stars. I hope it was interesting and exciting as I promised it was. There's a lot of similarity, at least particularly in the early stages of high mass star evolution as compared to low mass star evolution. But obviously there are some important differences in terms of the production of heavier elements, the onion-like structure that we produce in the core, and then the type 2 supernova that results at the end. And then finally the neutron star that we will certainly say more about in the lectures to come. So thanks for sticking with us here for lecture 20. Enjoy the rest of your day, whatever time it may be, and I will look forward to seeing you back here for lecture 21, where we finish up part 2 of the evolution of high mass stars.